For as long as human beings have looked up at the stars in the sky, two questions have captured our collective imaginations. Are there other life forms out there on any of their worlds, and will we ever realize the dream of traveling to one of them? Although both tasks appear to have enormously daunting technical challenges, recent advances in science suggest that not only might humanity be capable of overcoming them, but we might even do so later this century. While faster-than-light travel and visitations from aliens, whether benign or malevolent, are staples of our science fiction stories, it's plausible that our real-life scientific advances may legitimately be more profound than any fictional stories humans have dreamed up. On the edge of both frontiers, humanity may be on the cusp of achieving a dream as old as humanity itself. We all know that the biggest problem with the idea of interstellar travel is scale. The distances to even the nearest stars are measured in light years, with Proxima Centauri being our nearest neighbor at 424 light years away, where 1 light year is approximately 9 trillion kilometers, some 60,000 times the Earth-Sun distance. At the speed of the fastest space probes humanity has ever sent on their way out of the solar system, the Voyager 1 and 2 spacecraft, covering the distance to the nearest star would take approximately 80,000 years. But all of this is based on current technology, which uses chemical-based rocket fuel for propulsion. The biggest downside of rocket fuel is its inefficiency. 1 kilogram of fuel is capable of generating just milligrams worth of energy, as measured by Einstein's most famous equation, E equals mc squared. Having to carry that fuel on board with you, and requiring that you accelerate both your payload and the remaining fuel with that energy, is what's hamstringing us right now. But there are two independent possibilities that don't require us to dream up warp drive-like technologies that would rely on new physics. Instead, we can pursue the routes of either using a more efficient fuel to power our journey, which could increase our range and speeds tremendously, or we can explore technologies where the thrust-providing source is independent of the payload that's going to be accelerated. In terms of efficiency, there are 3 technologies that could vastly outperform chemical-based rocket fuel. The first one is nuclear fission. The second one is nuclear fusion. And the last one is matter-antimatter propulsion. Whereas chemical-based fuels convert a mere 0.001% of their mass into energy that can be used for thrust. All of these ideas are far more efficient. Fission converts approximately 0.1% of the mass of fissile materials into energy. Approximately 1 kilogram of fissionable fuel yields about 1 gram's worth of energy via E equals mc squared. Nuclear fusion does a superior job. Fusing hydrogen into helium, for example, is 0.7% efficient. 1 kilogram of fuel would yield 7 grams worth of usable energy. But far and away, the most efficient solution is matter-antimatter annihilation. If we could create and control 0.5 kilograms of antimatter, we could annihilate it at will with 0.5 kilograms of normal matter, creating a 100% efficient reaction that produced a full kilogram's worth of energy. We could conceivably extract thousands or even 1,000,000 times as much energy from the same amount of fuel, which could propel us to the stars on timescales of centuries with fission, or even just decades with fusion or antimatter. On the other hand, we could work to achieve interstellar travel via a completely different route, by placing a large power source capable of accelerating a spacecraft in space. Recent advances in laser technology have led many to suggest that an enormous, sufficiently collimated array of lasers in space could be used to accelerate a spacecraft from low Earth orbit to tremendous speeds. A highly reflective laser sail, like a solar sail except specifically designed for lasers, could do the job. If a large enough, powerful enough array of in-phase lasers were constructed, potentially reaching gigawatt power levels, it could not only impart momentum to a target spacecraft, but could do so for a long period of time. Based on calculations performed by Dr. Phil Lubin a few years ago, it's possible that speeds up to 20% the speed of light could be reached. While we don't yet have a plan for decelerating such a spacecraft, reaching the nearest star in a single human lifetime is within the realm of possibility. By the same token, the search for extraterrestrial life is no longer restricted to either waiting for an alien visit or searching the universe with radio signals for intelligent aliens, although the latter is certainly still an active scientific field spearheaded by SETI. Although no signals have been found, this remains a stunning example of high-risk, high-reward science. If a positive detection is ever made, it will be a civilization-transforming event. However, as exoplanet astronomy continues to advance, two techniques that have already been demonstrated could bring us our first signatures of life on other worlds: transit spectroscopy and direct imaging. Both of these involve using the light from a planet itself, with transit spectroscopy leveraging the light that filters through a planet's atmosphere, and direct imaging taking advantage of the sunlight directly reflected off of the planet itself. Transit spectroscopy relies on us having a serendipitous alignment of our observatory with both a target exoplanet and its parent star, but these alignments do occur, whereas a small fraction of the star's light will get blocked by the transiting planet. An even smaller fraction of starlight will transmit through the planet's atmosphere, similar to the sunlight that gets transmitted through Earth's atmosphere and lights up the moon in red during a total lunar eclipse. This enables us, if our measurements are good enough, to decode what elements and molecules are present in the target planet's atmosphere. If we could discover biological signatures, or even technosignatures, which could be an oxygen-nitrogen atmosphere, complex biomolecules, or even something like a chlorofluorocarbon molecule, we would immediately have a strong hint of a living world that would tantalizingly await confirmation. Direct imaging could provide exactly that sort of confirmation. Although our first image of an Earth-sized exoplanet likely won't be very visually impressive, it will contain a ton of information that can be used to reveal indicators of life. Even if the planet itself is just one pixel in a detector, we could not only break its light apart into individual wavelengths, but can look for time, varying signatures that could reveal clouds, continents, oceans, plant life greening with the seasons, ice caps, rotation rates, and much more. If there are light-emitting signatures at night, just as planet Earth has our light that illuminate the world at night, we could conceivably even detect those as well. If there's a civilization out there on a nearby Earth-like planet, the next generation of telescopes might be able to find them. All of this, together, points to a picture where a spacecraft, or even a crude journey to the stars, is technologically within our reach, and where the discovery of our first world beyond the solar system with possible life on it could occur in a decade or two. What was once solely in the realm of science fiction is quickly becoming possible due to both technical and scientific advances and the thousands of scientists and engineers who work to apply these new technologies in practical ways. However, note that in addition to building spacecraft like Starship Enterprise, there are some other interesting solutions to the problem of interstellar travel. You've probably heard the idea that black holes serve as gateways to other worlds, either distant parts of this universe or other universes entirely. Frankly, outside of the sci-fi realm, dropping into a black hole is a bad idea. Even so, it turns out that people who enter a black hole would have at least a slight chance of escaping, either back into their own world or to some exotic place. This is because black holes actually bend space itself, and so could bring points that are ordinarily distant from each other much closer together. An oft-used analogy is the bending of a piece of paper. If you draw a line on the paper, it follows the paper's shape, and the line's length is unchanged by bending the paper. But if you go through the paper, the end points of the line are much closer to one another. Understanding this requires diving into Einstein's theory of relativity as applied to gravity. It's important to understand that a black hole is not empty space, but rather a place where an enormous amount of matter is shoved into a teensy, tiny area called a singularity. In fact, the singularity is infinitely small and dense. There's actually some debate among scientists on this point, but more on that in a minute. As one moves closer to the black hole, the escape velocity, the speed needed to escape the black hole's gravity goes up. At a certain point, escape velocity is greater than the speed of light, or 292 kilometers per second. For comparison, the Earth's escape velocity is about 40,270 kilometers per hour at the surface. Since nothing can go faster than light, that means nothing can escape a black hole. But there's a loophole. A black hole doesn't suck up everything around it, like a vacuum cleaner or a bathtub drain. Its power extends only as far as the black hole's event horizon, whose radius is the distance from the center of a black hole beyond which nothing can get out. That radius gets bigger as more matter falls into the dense beast. Perhaps it's better to think of a black hole as a ball whose surface allows matter to pass inside, but never the other way. What's inside that surface is one of the biggest mysteries in astrophysics. Remember that most scientists think a black hole is a singularity. All the matter from whatever originally supplied the black hole's mass gets crushed into a point that has infinite density. If you were to fall into a black hole, the usual description of such an event says that you would first get stretched into spaghetti by tidal forces, then crushed into nothingness. Your matter would then add to the radius of the black hole's event horizon. Eventually, you'd be emitted as Hawking radiation. Physicist Stephen Hawking's calculations showed that black holes give off photons. In doing so, the black holes lose mass, because according to Einstein's famous equation, energy and mass are equivalent. Black holes eventually evaporate, but you would be waiting around a long time for that to happen. A black hole with the mass of the Sun, by cosmic standards that's a small one, takes on the order of 10 to the power of 87 years to evaporate and turn into a burst of gamma rays. The universe is about 14 billion years old. There's some debate in the scientific community about how long it takes for a black hole to evaporate, because the Hawking radiation doesn't preserve any information about the stuff that fell into the black hole in the first place. But the fact remains that being emitted as radiation is still not good. There might be a better way out of a black hole, though. Gravity bends space. To give you some perspective, let's think of a sumo wrestler rolling on a mat, indenting the mat with his weight. Any object creates a local gravity well. That well gets deeper toward the center of the object. A planet, for example, has a gravity well, but as you go toward the center of a planetary sphere, the well flattens out. Using the mat analogy, any normal object would have a well shaped like a depression with a finite depth. Black holes don't behave like normal objects. Perhaps fortunate for the trapped individual, the curvature of space just keeps going up and up until you reach the singularity at the center of the black hole, where that curvature is infinite. Instead of a depression, you just have a hole whose sides get steeper as you go toward the center until they are basically vertical and space is shaped like an infinitely stretched dimple. And that's why it's a mystery. Scientists use Einstein's theory of relativity to describe the curving of space, but Einstein's equations start to break down in the singularities of black holes. These singularities are also very small, and at that point, one should see quantum mechanical effects. However, nobody has worked out a way to make quantum mechanical theory work with gravity. To figure out what a singularity might look like, it gets even weirder when you realize that black holes aren't static. Realistically, any object in space tends to rotate. That means the singularity could, if it rotates fast enough, becomes a ring rather than a point. A ring singularity could provide a gateway to other universes, as in the 1994 sci-fi novel Ring by Stephen Baxter, published by HarperCollins. So, a black hole could be a wormhole, a gateway through space and time. The idea is so intriguing because when you have a point singularity, no matter how you travel, the singularity is always in your future if you are inside the event horizon. But a ring singularity can behave differently. The part that crushed you into nothing doesn't always have to be in your future because of the weird ways a ring singularity would bend and twist space and time. However, The concept of a ring singularity as a gateway is far from a sure thing. First, nobody knows how a ring singularity would come into existence. The other problem is that whenever people have tried to work out the mathematics of a black hole made wormhole, they run into problems of keeping the gateway stable. Wormhole are ridiculously unstable. The moment even a single photon or light particle enters, the whole wormhole catastrophically collapses before that packet of light can escape. Which brings up the fundamental problem. While most scientists say black holes can be wormholes, without a theory of quantum gravity, such questions are hard to answer conclusively. So, maybe a new, improved theory of gravity would allow wormholes to exist. Interesting information, as the search for extraterrestrial life is a daunting task, especially for a human. We've got some non-human intelligence to join the search. The use of AI is reaching critical mass in our everyday lives and in science, so it is no surprise that it's now being employed in SETI. Of course, we're not talking about Skynet, or the machines from the Matrix movies, or even Star Trek, the next generation's data. The AI that is so in vogue at present is based on machine learning algorithms designed to do very specific jobs, even if it's just to talk to you on ChatGPT. To explain how AI is assisting in SETI, astronomer and SETI researcher Eamon Cairns of the University of Manchester compares it to the needle in a haystack problem. You basically treat the data as though it's the hay. Then you're asking the machine learning algorithm to tell you if there is anything in the data that isn't hay, and that hopefully is the needle in the haystack, unless there's other stuff in the haystack too. That other stuff is usually radio frequency interference, but the machine learning algorithm is trained to recognize all the types of radio frequency interference we already know about. Those signals, the familiar patterns of mobile phones, local radio transmitters, electronics, and so on, are the hay. According to Steve Croft, an astronomer with the Breakthrough Listen SETI project at the University of California, Berkeley, the training involves injecting signals into the data, and then the algorithm learns to look for signals that are like that. The algorithm learns to spot the patterns of these familiar signals and disregard them. Should it spot something in the data that it hasn't been trained on, then it flags this up as something interesting that requires a human to follow up on. This project was led by Croft and Peter Ma of the University of Toronto, who wrote the algorithm and put it to work analyzing data from 820 stars observed by the 100-meter radio telescope at Green Bank Observatory in West Virginia. The data, totaling 489 hours worth of observations, contained millions of radio signals, almost all of which were human-made interference. The algorithm checked every single one of them and found 8 signals that did not match anything it had been trained on and which had been missed by earlier analyses of the data. These 8 signals seem to come from 5 different star systems, although they might be misleading. They haven't been detected since to see a signal repeat is the most basic requirement for a signal to be considered interesting in SETI, and they will probably turn out to be more radio frequency interference. However, even that's useful, because they can be used to train the next generation of machine learning AI, so similar radio frequency interference can be avoided in the future. Machine learning algorithms can be divided into 2 camps. One is known as supervised learning, which is the teach it, everything you know approach. Unsupervised learning is a little different, in that you just feed the algorithm the data and let it figure out what is significant, without any human biases. As a mundane example, suppose you have a data set of images of tables and chairs, and you want the algorithm to distinguish between them. In supervised learning, you train the algorithm on lots of images that are marked table or chair. With unsupervised learning, the algorithm has to distinguish between the two by grouping things that look similar without any prior training. For example, it might select anything with a back to be a chair, and anything with a long top to be a table. Cairns highlights the example of a project led by Adam Lesnikowski of NVIDIA, who are famous for their graphics cards, but which are now leaders in artificial intelligence. Lesnikovsky, joined by Valentin Bickel of ETH Zurich and Daniel Angerhausen of the University of Bern, used unsupervised machine learning in a test to see whether it could spot artificial objects on the moon. The algorithm was fed images from NASA's Lunar Reconnaissance Orbiter, and it had to figure out what was a typical lunar feature, such as a crater or a rill, and what wasn't. The test was a success. The algorithm picked out the Apollo 15 lunar lander on the surface of the moon. The idea is that technological aliens may have already visited our solar system and left probes or artifacts on the planets, moons, or asteroids. It's possible there may even be an active probe watching us right now. Some researchers are very interested in the idea of having orbiters with a machine learning algorithm on board. A spacecraft could survey planetary surfaces in our solar system to search for anomalies that could be alien probes, possibly millions or billions of years old now. Because unsupervised learning has the advantage of being able to function in real time, it would be able to assess each image before moving on without having to wait to send all the data back to Earth for humans to look at. Certainly, in the age of big data, machine learning AI is the way forward and is now being used extensively in astronomy and in SETI, with the capability to do things faster and better than humans can. With machine learning algorithms, humans are still intimately involved. A signal might get flagged up by the AI as being intriguing, but it is still humans who have to follow up and investigate. The algorithms aren't that smart. A time may come soon, however, when they are that smart. Researchers at places such as Google DeepMind have been pursuing artificial general intelligence, or AGI, whereas the algorithms we have today are very specific. AGI would be able to cast its hand to anything and learn and grow while it does. An AGI could rapidly accelerate beyond the capacity of human intelligence. The possibilities for AGI transforming SETI are tantalizing. We've already seen how machine learning algorithms designed to play games such as chess or Go are developing strategies that befuddle the human experts whom the AI is beating in these games. An AGI could surely think of new ways in which to search for alien life beyond the confines of human biases and experience. As Karen said, it would be able to map out all sorts of possibilities for how language and communication can be conveyed through signals. It might be able to consume vast astronomical catalogs and decide on optical strategies on how and where to look. Steve Croft echoes Karen's optimism. He, hope AI evolves to the stage where we can ask it to take the blinders off and imagine from everything it knows about physics, biology, chemistry, exoplanets, and technology, what it thinks extraterrestrial might be doing. It will probably come up with some good ideas. That's if it can or even will tell us anything. The creation of an AGI will, in a way, by like creating an alien, one that is very much unlike us and which we might struggle to understand. But that's just speculation. In the here and now, AI is a powerful tool that is accelerating our searches for extraterrestrial. It's a sure thing that if we do discover a signal from another world in the future, we'll have AI to thank for it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.